Welcome back to the second lecture of design and analysis of algorithms. So in the previous lecture, lecture 1, we saw that what is the definition of an algorithm and how to design. We also saw how to design an algorithm and what is the meaning of design, what is the meaning of analysis, and how design and analysis of algorithms play a significant role in the computer science and engineering. So we also saw how to calculate the computing time of an algorithm. So we used a priori analysis and a posteriori analysis. So we also saw how to calculate the time using the counter, right? So we also saw that using the a priori analysis and also the a posteriori analysis. So a posterior analysis was we discussed two methods. One is with respect to the clock time, okay, which is available in the programming languages. The other one is with the use of the counter call time. So every time, based on the number of operations in a given instruction, so time will be incremented. So if the number of operation in the operations in the instruction is 2, then time will be time equal to time plus 2. So this is how the computing time is calculated for the algorithms. So in this particular lecture, which is the lecture 2, we will see some algorithms, okay, some interesting algorithms and different versions of algorithms. For example, here what I have taken is the multiplication of two numbers. So we will see different 3 to 4 types of algorithms for the same problem, right? So now let us begin this lecture with the problem of multiplication using the lookup table. Okay, so now I want to develop a lookup table for the multiplication from 1 to 9, right? So 1 to 9 are the numbers, and I want to have the answer for I want to design a data structure like this, okay? And in the worst case, what can be in the worst case? Suppose I want to store the answers of all these tables of from 1 to 9, then you can see here that 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3, similarly 1 into 4 is 4. This is the table of 1 and this is the table of 2. So 2 into 1 is 2, 2 into 2 is 4, 2 into 3 is 6, 2 into 4 is 8, 2 into 5, 10, similarly it goes on. So in the worst case, what can be here is that this whole space, right? In order to store these tables of 9, I can means I must have 9 into 9, that is 81 locations, right? So I need a memory of 81 locations. So what I have done is that you can see that I have not added, means I have removed the redundant computations. For example, 2 into 1, okay, 2 into 1 is 2, 1 into 2 is also 2. So I have not written, right? So I have removed this one. So this is an efficient way of representing what I can say, that multiplication of 1 to 9, right? Numbers from 1 to 9, and this is the these are all the redundant computations. So this have been removed. So now the interesting question comes: how can we design an algorithm to look up, means to get the answers for the multiplication? Okay. So now if we see, if we already studied the programming language, right? So now if you want to implement this particular idea, then we usually declare an array of suppose this maximum size is 9 into 9, it is 81, right? So the 9 into 9 matrix we try to define, and then we can store it and this. So now here we'll see some efficient one. What we'll do is that, should we use two-dimensional structure two-dimensional data structure to solve this problem, right? So the answer is that right. So answer is no, right? We can use one-dimensional, and in two-dimension we saw that the memory requirement is 81 locations we need. So now let us try the same idea using one-dimensional array. So what simply I'll do is that, see, in one-dimensional array, I will store like this. You can see that in the first location 1, 2, 4, 3, 6, 9, 4, 8, 12, 16, 5, 10. So continuously I'm storing like this: 10, 15, 20, 6, 12, 18, 24, 30, 36, 7, 14, 21, so on, like this. Okay, I will store. So how many, what is the maximum size of the array? The maximum size of the array will be around 45. So these are the locations. Please don't confuse this one. These are the location numbers: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the 11. This is 12th location, 13th location, 14, 18, so on up to 45. So now what I have stored is that I have stored all those answers, right? The answers 1, 2, 4. Now, if you see, right, now I have now the locations here and the answers here, right? So now, for example, we want to derive the fourth, like for example, this is the 12. So this 12 answer is 4 into 3, right? 4 into 3 is 12. Similarly here, you can see that 6 into 2 is 12 here. Here 9 into 9 into 8 is 72 is here. 9 into 9, 81 is here, right? So we have to intelligently sort out that table of 4 starts from which location, table of 3 starts from which location, right? So we will just see it, we will intelligently, we will peep through this data structure and we will devise, okay, we will develop a general way of solving this, the representing this particular problem. So now let us see again. So this is the table which was already given. We have stored all the values of the lookup table in 45 locations. So for example, now let us try to develop see some instances here. So for example, 4 into 3, right? So for the table of 4 into 3 is 12. So this 12 is in what position? This is in the position 9, right? Suppose let us take that this is m, this is n. So if you want to have that 4 into 3 is 12, it is in the position of 9. So 6 into 2 is 12, answer is 12, it is in the position 7. 5 into 4 is 20, it is in the position 14. So can we develop a general algorithm or a general model to just, if we know m and n values, we can directly pick up the answer from the table, right? So 9 into 8 is 72 and 72 is at the location 44. So now in general, I can represent this as m into n, which is mn. So what is the position of, okay, what is the position? Can we automatically calculate this position from this given m and n values? Yes, it is possible, right? So now what can we do is that now again, moving further, so suppose, for example, this is the, so let us see that what is the starting point of the table. So table of 1 starts at location 1, table of 2 starts at location 2, table of 3 starts at location 4, table of 4 starts at location 7, table of 5 starts at location 11, table of 6 starts at location 16. Similarly, so table of m will start at the location m into m minus 1 divided by 2 plus 1. So if you have already seen the structure of that lookup table, you might have already guessed what is the location starting point of the tables. So now let us go further, right? So now let us move forward. So if I have the table, so let me represent this, okay, this as n and this as ml. Now I want to generate the table of m, okay, m. So m into 1, m into 2, m into 3, m into n. So m into 1 can be, okay, it can be found at the location m into m minus 1 divided by 2 plus 1. Similarly, m into 2, m into m minus 1 divided by 2 plus 1 plus 1, right? So now this becomes m into m minus 1 divided by 2 plus 2. Similarly, m into 3 is m into m minus 1 divided by 2 plus 3, so on. If you calculate, and then you can see that m into n will be at the location m into m minus 1 divided by 2 plus n. So this is what is the okay, this is what is the general formula for the for fetching the answer, right, for the multiplication of the table using the one-dimensional array. Hope you have understood this one. So now, yes, so there is a time-space trade-off in this formulation. Okay, there is a time-space trade-off in this formulation. Like for example, if you represent using 2D array, then you require 9 into 9, which is 9 square, 81 locations in case of 2D array, whereas in case of 1D array representation, we require 9 into 9, 9 minus 1 divided by 2. So it is lesser number of locations we require. The array size gets reduced here, and it is 1D array. So it is n square versus n square divided by 2. Okay. And regarding the access, it is, we require how many pointers? We require 2 pointers, that is m and n are the 2 pointers which need to be accessed in order to get the answer. Whereas in this case, since it is a single dimensional array, we require only one single pointer. So these are some of the time and space trade-off in this particular algorithm. So now let us continue with the multiplication problem, right? So this is a high school maths which we have, which we are all familiar. Okay, so given two numbers, right? Given two numbers containing digits. Okay, so here it is 3 digits. Here it is 3 digits. Here it is 4 digits. So now, how do we do multiplication? So our teacher in the high school, they have taught us that we take numbers, like for example, we start from the left location, right? So we start from the rightmost location here, that is the 4, and we start with the rightmost location in this particular. So we require, the answer is we require 2 pointers, right? So 1 pointer for this particular, okay, this particular these 3 digits, and we require 1 pointer for this particular 4 digits. So now let us see. Let us now try to store. So now to store the answer, to store this answer, I will be requiring a 2-dimensional array. Okay, and intelligently I will put up the answers here, and then I will calculate what is the answer of multiplying this 3 digit into this 4 digits, right? So what is the answer? So now let us start. So let us have 2 pointers, one pointing to the rightmost digit here, right? That is 4, and we will have one more pointer, that is green, which is the rightmost digit of the the first number which we want to multiply. So now let us start multiplication. So 4 into 1 is 4. So now we know that we need not do any adjustment here. Directly whatever the answer we get, we'll store it here. So now you can see that 4 into 1 is 4. 4 into, okay, so now 4 into 1 is 4. Now we know that 4 into 8 is 8 into 4 is 32. So 32, I cannot store 32 here directly here. So I require, right? I require an additional memory where I can store the carry bit. So I tell this as a carry bit, and I store 3 here and then 2 here. So next number is 4 into 9. So 9 4s are 36. 36 plus 3 is 39, right? Again, carry 3 is generated. So now since there is no other number here, so 4 into so this 3 carry will go and will sit in this particular position. So now what is the next step? So in the next step, this pointer, the green pointer, will be reset, right? The green pointer will be reset to the starting location, whereas this pointer, which is the pink pointer, okay, this pointer will move to the next position, that is the position number 3, right? Here it is a position 1, position 2, it will position, so the pointer will come here. Now we know that if we try, when the pointer moves 1 on the left side, we should also block one location here, right? So this is what is the convenience we have been using in our high school method. We will block this particular location because, okay, we have moved the, so this particular position is blocked when we have moved the pointer. And now see the simple multiplication from 3 into 9 8 1, right? We will simply multiply 3 1 3, 9 8 3 is 24, so 24 2 as a carry, and then 9 3 is 27. 27 plus 2 is 29. Okay, so 2 is generated, and similarly now we got the answer, right, for the second digit here for 3. So now the pointer, similarly this green pointer will be reset to the starting location, and then now this pointer will be incremented, and the pointer will be now moving to the this digit. This is third digit here, right? So now same when the pointer is moved to means here 2 digits here, then I should block these 2 locations and then store the answer. So I will multiply 2 into 1, 8 to the 16. So 16 into 1, 9 into 2 is 18. 18 plus 1 is 19. So this is 19. Similarly, the pointer will move again here 1. Again, I can see that I have to block because I have moved these 3 positions here. So my pointer is, since my pointer is here, I have to block these 3 locations. So again, I multiply 981 into 1. So you can see that the answer is 981. And now the stopping condition, right? We already saw that your algorithm should end. So the ending will be that this pointer, you can see that here, the pink pointer here, the pointer, there are no more digits here, right? So there are no more. So now this is a terminating condition. As the number of digits have been exhausted, then your algorithm would end up. So now it is the next step. In the next step, it is to add all these numbers. So it is very we can just end this one, and now we can simply see that we will add these numbers, right? All the numbers within the column. And again, you can see that again I need carry because there may be condition, like for example here we are lucky that we have only one number, but whereas here also we have only single digit, but here we have 2 digit, but we require the carry bit here, right? So it is 4, 5 and 9 plus 4 plus 2 is 5, 15. This again 1 is the carry, and again I will add it. So it is 20, and again it is 21. So 21, 9, 10, 11, 12. So again, one more carry is there, 12. So this is the answer. So now we are seeing the working of this beautiful algorithm in the pictorial form. But now, how can we implement this? How can we write algorithm such a way that we do all these techniques, right? All these ideas which we have shown through this illustration. How can we use it? How can we program it, right, to get this answer? So that's a very, very interesting. So we need to write the program. So now this is the algorithm number 1. So now can we think of representing the same multiplication in any other way, right? Can we do it randomly? Like for example, in this case, what I have taken is that I have taken 4. I have taken the first digit and multiplied with the 981, right? I have multiplied. Similarly, I have taken the 981 into 3 and I have followed sequence of it. So can we do it randomly? Can we? So if you see this structure, can you guess that I can write this algorithm in any other form? Yes, you can write it. For example, so you can simply start with this location. For example, this 1, you can start your pointer we have started the pointer from the rightmost, and now let the pointer start from the leftmost, right? So it is 1. So simply, but keep it in mind that when you start from here, you have to block the number of digits which are on the right side, right? The number of digits which are the right, that should be blocked. So now you can see that I can calculate 981 first, right? So the next algorithm, you see that 981 is calculated first, 1962 is calculated the second, and so on, right? I get the same answer. So this is another way of implementing the same algorithm. So now you think, what is the time complexity? What is the space complexity? Whether there is any advantage? Can it be done randomly, or can I randomly start at any pointer here, and then I will do multiplication. So this is the algorithm number B. So now by looking at the idea of multiplication, right, the algorithm which we have discussed, so some questions come, right? So can the parallel implementation be possible? Okay, so can I have 4 so for example, in this case we can see that, can I have 4 people? Like for example, I want to multiply 981 into 1, 2, 3, 4, right? 1, 2, 3, 4, I want to multiply. So can I give, for example, can I give 981 into 1 to one student, 981 into 2 into 2 to the second student, and 981 into 3 to the third student, 981 into 4 to the fourth student. So I will give I will give this one, right, the individual multiplication, and I will tell, please give me the answer. So my job will be that to remember that I have given this particular digit, right, 981 into 1 to the first student. So I would keep my structure ready, and as soon as I get the answer, I will just put it inside the table, and then I will add it, right? So can the parallel implementation, can we fill each individual row concurrently? That's what is I discussed, that can we give each individual multiplication to the students, right? And can we take the answer and we add it simultaneously, right? So that would be possible, right? So can we add the individual columns concurrently and just wait for the carry from the lower significant column? So these are some important questions, okay, the important ideas which we need to ponder over it. So study the speed up, can decrease in computing time, increase in number of processes. So what will be the impact, right, of the computing time on in such cases? So observe number of processes and the computing time trade-off. So when you increase the number of processes, what is the computing time? Whether there is decrease, whether there is increase, okay, what would happen? We should do analysis of all these ideas. So now coming to the same multiplication problem, right? The multiplicand and the multiplier. Here 981 is a multiplicand. Here 9 1 2 3 4, same numbers, 3-digit and 4-digit numbers we have taken. So now this is the second, this is the third algorithm which we are going to discuss, that is the C here. And so the algorithm is very simple. Simply what we'll do is that we'll follow these steps. Okay, we'll just try to understand these 4 steps, and in the next slide we will try to solve the try to implement this idea, right? So now given 2 numbers, multiplicand and multiplier. So write the multiplicand and multiplier side by side, right? You make 2 columns and you write down. So create 2 columns, one under each operand, by repeating the following rule until the number is left. A number in the left hand column is 1. So what is the terminating condition? Terminating condition is that until the left hand column, the number in the left hand column is 1, right? So now you divide, that is truncate the number in the left hand column by 2. So simply you half the number, right? You half the number, you make it half, okay, and then double the number in the right hand column by adding it to itself. So here I am dividing by 2, and there I am multiplying by 2. So cross out, this is very interesting, cross out each row where the number in the left hand column is even. So if the number in the left hand column is even, you just cross it over. I don't need that to be added up, right? So that you cross it up and add up the numbers that remain in the right hand column. So leaving all those striked out columns, you simply add all the answers, right, all the numbers, then you will get the answer for the 981 into 123. Let us see with an example here. So I created 2 columns, left hand column and the right hand column is here, right? Left hand column, right hand column. So 981 is multiplicand, multiplier 1 2 3 4. Here I am just making a pointer to check whether it is odd, because once it is odd, then I will strike out this particular row, right? And this is the answer. Okay, so now let us see. So what I have done is that 981 is made half, right? Is made half, so it is 490, and 1 2 3 4 is now doubled here. So this is made half, this is doubled, and now I know that this is the even. So this number is even. So once it is even, then I need to strike it out, right? So I need to strike it out. So it has been, so this is not needed. Now let us continue. So 490 again half, 245 again, this is doubled, but this is not an even number, this is an odd number. So I will retain this particular value. Similarly, continue again, 245 again half, it is 122, 9872. Yes, this is even. Strike it off. When it is even, this row you strike it off. Similarly, 61, 19744, it is odd. Yes, you retain this. Similarly, 30 and this 39488, it is even. Strike it off. Similarly, move forward and I get 15 here, 78976. It is odd column. Retain this one. Further, I get 7. And here I double it, and this is odd, so I will retain this. Similarly, I make it half, that is 7 divided by 2 is 3 here. Okay, approximately here it is 3, and then we can see that this is doubled and it is odd, so I retain this value. Similarly, at the final, this is 1, and this is doubled value, this is odd, and then I should retain. So now what is this? This is the stopping condition. The stopping condition is that if the left hand side column is 1, then you stop it. And how to get the answer? Simply calculate, simply add all those numbers in this particular column, add all those numbers, and then you can see that this is a stopping condition and this is the answer, right? 1210554, this is the answer of all this. So this is one interesting algorithm. So can we implement this algorithm, right? Can we develop an algorithm to solve the problem in this way? That's right. So no need to have multiplication table. So this is very, very interesting that this particular idea, okay, it does not use any multiplication table and need only to know the only halving or halving or doubling, right? So we can we only need to just half the number and double the number. So parallelization may be difficult here because the output, the input, the current step, see here there are no independent steps. So every next step is dependent upon every current step is dependent upon the previous step. So parallelization may be difficult here. And now let us see the fourth way, right? The fourth approach, that is we can see here, right? The fourth approach to solve the problem is using the divide and conquer approach. So divide and conquer approach we will be learning. We will be diving into in more detail in the coming lectures. But here, just to give you the idea that same problem can also be implemented using divide and conquer. So what I do is that I have multiplicand and multiplier, right? So both multiplicand and multiplier should be. So there are certain conditions where this algorithm would apply, right? So before applying, we should check whether these conditions are met or not. So both multiplicand and multiplier should be positive integers. That is the condition. Both should have the same number of digits, and the number of digits should be a power of 2, which is in 1 digit, 2 digit, 4, 8, 6, like this. Okay. So then only we can use this particular approach. Now, for example, coming to our previous example, 981 multiplied by 1234 should be written as, for example, here there are 3 digits, but it should be in the power of 2. So I make it as a 4. Simply I add it as 0981 into 1234. So now how will I solve this problem? So I think the method here, divide and conquer, itself tells that there are 4 digits here. There are 4 digits on this side. So now let me divide this digit into 2 means digits of 2. So for example, here let me take this just to explain you. So now let me take this digit, right, and this digit, right? So now you can see that so 09, okay, 09, which is 09 multiplied by 1 2 and 09 multiplied by 3 4. So I am dividing this multiplication. So 09 is multiplied with 12, 09 is multiplied with 34. This is what I am, and then 81 is multiplied by 1 2 and 81 is again multiplied by 3 4. So I am dividing this whole multiplication into 4 steps. So now you can see here in the next slide, you can see that 09 is multiplied with 12, 09 is multiplied by 34, 3 4, 81 is multiplied with 12, 81 is multiplied with 3 4, right? So now one more very interesting thing which you should remember is that once you multiply, for example, here you multiply 09 into 09 into 12, right? You multiply. So, but you should also ensure that how many digits you have means shifted here, means you have left here. So here there are 2 digits, here there are 2 digits. So you must leave 4, that 4 shift operations are required here. So for example, if you take this 09 and 12, then you should ensure that you leave 1 2 3 4. 4 shift operations are required here. Similarly, now once you deal with 09 and 3 4, then you require to shift only two digits. So that's how you should remember that as we select the digits, so we should also compute what is the number of shift which is required. So for example here 0, 9, 12, okay, which are the leftmost two digits, right? So 4 shift is required, and I will just leave this 4 dots. 4 dots means 4 shift here, and I would simply put the answer 108. Similarly 09 into 34, 306. So this is, there are 2 shift here. 81 into 12, there are 2 shift here. 972, 81 into 34, right? 81 into 34, there are no shift here. So simply you add these results, right? Simply you add these results. Now another interesting question. So now there are two digits, right? Here 2 digits, here 2. Now let us, can we further simplify this? For example, 81 into 12. So 81 into 12, can we further simplify it into multiplication of single digit? Can we do it? Yes, we can do it, right? So for 4 digits split into digits of 2, 2 digits again split into digits of 1. So now let us see how, like for example 81 into 12, we have got 972. Can we split this 81 into 12 and get the answer 972 in the same fashion? Yes. So let us do that. So what I will do is that, you already know that 8 into 12, suppose you want to multiply, then this 8 will be, right? Let me select the pen here, right? Sorry. Yes. So this 8 will 8 into 1 and 8 into 2, 1 into 2 and 1 into 1 into 1 and 1 into 2. So these are the 4 multiplications which I should do. So same thing is shown here. So you can see that 8 into 1 is, okay, 8 into 1 is 8. There are 2 shift here. 8 into 2, 16, 1 shift, 1 into 1, 1 into 2. You can see that I got 972 here. So that's what we have generated. You can see that 972. So this is the approach where we take a bigger number, we divide the number, and we conquer it, right? Conquer means we go in the backward fashion to get the overall answer. So that's how here. So now the questions are that, check for any other method for multiplication, whether there are some algorithms, you can just bring it up, right? So make a comparative analysis of different approaches. So now the interesting thing, you have developed the 4 versions of the same problem. So now try to come up what is the time and space trade-off, what is the computational complexity, try to do profiling, right? So try to do the parallel implementation, like for example A, B, D algorithms, right? So you can, these 3 algorithms you can try to do parallel implementation and see the performance based on the number of processors, right? So there are some assignment problems. So you can just go through the book of R.G. Drome, and you can see that some interesting algorithms here. Okay, these algorithms you can just see it. Okay, right, and try to think over it, right, to solve. So in the next lecture, we will come up with some more advanced algorithms, right? And we would also discuss some strategies in the upcoming lecture. Thank you.